So, let's get started here today. Excuse me. We're talking about tangents today. It's a brand new topic for us, but I don't think we've talked about in this class. You probably talked about maybe in drafting if you've taken that class. But tangents is kind of an important topic. In fact, I hinted at it, we just never discussed it. So here's the idea. If you had a circle, okay, so here's my circle with a center of C, and you were to draw a line, like has two arrows, goes forever. Draw a line, but it only hits the circle perfectly once. That's a tangent. So a line that somehow can perfectly touch the circle at one location like that. Like one spot, didn't cross twice, hit it perfectly right on the edge. That's a tangent line. Okay. Or a line of tangents. Okay. Now, how they label it, again, usually the book uses like cursive letters, like they call it line L. If they had 2 points on the actual line itself, let's call this point down here, let's call this A, and we'll call this point B. You could call it a line AB. You could call it line L. These are the options you have since day one of this class. Those are ways you can write lines. But again, the definition of a tangent, it's a line that intersects a circle exactly once. So in fact, let me put that up here. It's a line that intersects a circle exactly once. Okay. And the idea with the idea of exactly once is that if it's a true line, that means it goes on forever. So you would actually have to draw a arrow so it kind of goes forever. So like it won't hit a second time. It's only perfectly grazing it. So that's the word tangent. Now the second word we have up here is called the point of tangency, and that is this spot right here. This is the point of tangency. It's that spot, point B, namely. That's how you name it. You say actually point B. But the actual point of tangency is that location where it actually touches the circle. Okay, so those are the two major vocab words here. Now, I've hinted at the fact that I've actually discussed tangents before. I never really give you the formal definitions, and it came up with the day we talked about the bicycle, and we were talking about if you were to change that sprocket where the pedal is at, and it's attached to the sprocket in the back where the back wheel is, that you can go faster, right? We talked about how bicycles basically work. Well, the chain itself that connects the sprockets, the chain, is actually a line of tangency, because it touches the sprocket at exactly 1 point on both parts. So in fact, let me draw that. So like on a bicycle, you have that back sprocket, you have that front sprocket where your pedal's at. The actual chain itself, this is a common tangent. It is a line that is tangent to both circles at the same time. Now there's two types of common tangents. There's two types, but usually this is what most people think of a common tangent. You could have the situation where the tangent actually goes in between them, like this, where the line is like directly in between, so the two sprockets are actually physically connected to each other. A really good example of this is how a printer works. They push two wheels together, and then the wheels feed the paper right through the printer. So the idea is that you have two circles, and the piece of paper is actually the line of tangency going right through. Notice that common tangent line. And then sometimes like in a pulley system, a pulley system can work like this, or you could have like a belt system in like a car, a vehicle, where the common tangent can be through the inside, like that, where it actually touches both circles perfectly once through the inside. And then obviously the belt would wrap around. That's how timing belts work and serpentine belts and all that good stuff. So the belts in the car are a little more complicated than they tend to look. But that's kind of the concept there, that you have multiple items in the car itself, like the fans and the actual motor itself, and all the belts are connected to them, so they all run at the same time and the same speed. So if you're pushing the car faster or harder, it speeds up the fans to cool it off. I mean, it's pretty clever the way the system actually works, but that's the idea. It's a common tangent.
What is its definition?
Common tangent is a tangent line that intersect both circles exactly once. So it is a line that is tangent to both circles at exactly like one spot.
Would it be tangent to more than 2 circles?
What?
Would it be tangent to more than 2 circles?
Yeah. Oh, yeah. You could have like 3 to 4 circles. Yeah. So a good example would be like an assembly line. If you're like putting something down like a rolling cart that rolls, they could have multiple tracks there, tangents to object that like sails across them. Like Bill's Foods up here in town, they have that belt that feeds like the conveyor belt that feeds all your like groceries across. There's multiple like rollers that are underneath it, so the belt itself is tangent to all of them. It's like rolling across the top. That's the concept. Okay. That very thing is actually how they believe that they moved very large stones for like ancient civilizations to like set up like the pyramids and other things. That you actually just put like logs or very smooth surface objects that are underneath it that can roll on the ground, and that's how you can put an object on top and just roll it along. The idea is that, let's get rid of this picture, that I know this is really archaic, but it's actually how like modern day people move objects, like hot tubs. I used to set up hot tubs during the summers and stuff. The idea is that a hot tub's really heavy. It's like 5,600 pounds or something like that. Something stupid. They're crazy heavy. Well, to get a hot tub from like a trailer to the backyard where most people want them, you actually just put PVC pipe on the ground, like just a couple. You have like 5 or 6 of them, and you place this super heavy thing on it, and you push it, and it just rolls super easy. Like you could just push it with one hand, and it just rolls across the ground. And then all you do is like once it's past a certain point, you pick up the back one, put it over here. So you just have like 3 people doing it. The only hard part is once you get there, then you have to like put it on the ground without killing yourself. So, but it's actually really simple. And this is like the concept you're seeing there is stupid. It's like archaic. That's how they believe that, you know, they move very large rocks for like ancient civilizations and stuff. It works. I mean, I'm a testament to it. I've seen it work for a hot tub, so I can only imagine what it can do for a very large boulder. So, questions, comments about what a tangent is? Okay, all right. Let's go through a theorem here. I only got 2 theorems I want to talk about today, and we'll try to prove them. All that. The first one is a biconditional statement. It uses the words if and only if. So, we're going to do theorem 10.10. Okay, I don't think they have a name on this one. I don't think it's called like the tangent theorem. Nope. No. In a plane, a line tangent to a circle line tangent to a circle that's weird. Alright, in plane, a line tangent to a circle if and only if the tangent is perpendicular to the radius of the circle drawn to the point point of tangency. Drawn to the point of tangency. There. Okay. Let's write that down. This exact wording from the book. I always find that word that if and only if. That just doesn't seem grammatically correct to me. The way they use it. All right. Okay, so you have a plane, like a flat surface like my marker board. You're going to have a line that is tangent to a circle. So it only hits circle once, that's the definition of tangent. But what they're saying, if and only if, that tangent line actually turns out to be perpendicular to the radius. So 90 degrees to the radius. That's the only way you can actually draw a tangent line. And that radius has to be drawn to that point of tangency. So the goal is to actually show you that. So let me draw this, and we're going to try to prove it. I'm just going to try to use some logic. Since this is an if and only if statement, it actually can go both directions. So, all right. Here's my circle. Okay, let's call this circle C. And we have a tangent line over here. And let's call this A. And what they're trying to say is that if this is truly a tangent line, let's call this line L, like for tangent, right? So line L. If that's truly a tangent line, then this angle has to be 90, right where that radius meets that point of tangency. That's what they're trying to say. Question?
And you can move the radius around, right?
Yeah, you can move the radius kind of wherever you want, but they're saying that if you're to put that radius perfectly so it hits that point of tangency, that point A, that angle with the tangent line and the radius has to be exactly 90 degrees. That's what we're going to try to show. Okay, and there's two parts here because it's an if and only if statement. Yeah, so the idea is that if you have a tangent line to a circle, right, a tangent, then that angle has to be 90 there. And vice versa, if you have a line that is tangent to the radius, then it has to be the tangent. So it's like backwards and forwards. So the idea is I'm going to show one direction and then the other direction. So here's the idea. We're going to start with the fact that let's assume that that angle is not 90. Okay, so we're going to start with that idea. So what I'm doing here is called an indirect proof. An indirect proof is where you start with the assumption that whatever they wrote was technically wrong. Like this is wrong. So you start with that fact that it's wrong, and then what you do is in the very end you show that you try to go with that idea that okay, they're wrong, and you try to show why they're wrong, and at some point down the road you find out that they're right. Right? It's common logic. Like you argue with people enough that you're like you believe like what you want to believe, and people are saying otherwise. And then eventually down the road, you're like, oh yeah, they were actually right. I shouldn't have done this, right? It's something like, it's called an indirect result. So that's what we're gonna do. We're gonna assume that that is not 90. That maybe some other point down the road, that was 90. I know, I'm really exaggerating that picture. So that maybe this point B down the road, that was actually the 90-degree mark. That it wasn't actually at the radius, it was like some other point down the road. Okay? Does that make sense what I'm doing? Okay. And we can call that B. Okay? Alright. So here's how it works. And this is like the easiest way I can explain that to show that this line has to be like, the radius has to be like perpendicular right there. Like that spot has to work. Okay? Alright. So what I'm going to do, is this is going to be a little weird, I'm going to do like a construction style proof. I'm going to go on the other side of B. Let's go down the road, other side of B. Let's find this point D down the road. But I want to make this part right here equal that line. They're the exact line. So I can copy that, right? I can keep drawing that line straight. I can take a compass, measure this out with my compass, like open it up so the point and the pencil, and then copy that distance over here. Right? So it is a construction. And then I'm going to draw a line to there. Now there's a rhyme and reason to my madness here, but I do want to talk about what this is. So. Okay. So if this is true, like that maybe some other point, not A, but some other point down the road was perpendicular. And you know, I went some distance down the road to find that point, okay? What I can actually do is I can actually prove that this triangle and this triangle are actually equal to each other. That the two triangles are side by side, okay? Because they both have right angles technically, because that is a straight line, so that this is a right angle, that's a right angle. I both have AB and DB are the same distance, and both triangles share the stick in the middle, correct? That's called the reflexive wall. So by side, angle, side, the two triangles have to be equal to each other. The two triangles have to be equal, okay? So this triangle and this triangle are equal. So if the two triangles are equal, we have those walls and you know this wall, then that forces this third wall to be equal to that third wall. If the two triangles are equal. You guys get the idea there? That they have to be the same triangle. Well, if you look at the blue line and the black line, are they the same length? No, I have a problem with that. Like that's a major issue. This is the moment where you go, oh crap, I didn't do something right? Like if friends were telling you not to do something you did, you're like, I'm not gonna believe them. This is the moment you poop yourself and you're like, I just figured out I shouldn't have done this in the first place. This is it. Because here's the idea. If this distance is the same as that one, that blue line, which is not, you can see it's terrible, then this is a radius. That's a radius of a circle. So then that means this blue line should be a radius. Should be, in theory. So, because it's the same length as A to C. Well, did D end up on the circle? No, it couldn't have landed on the circle. Because if that's a true radius, then that means that thing should have been here. And that means the stick would have been doing this. That means it would have hit the circle twice, not a tangent line. So I just disproved it twice over. Like the picture looked terrible, but then it wouldn't have been a tangent line. It would have actually hit the circle twice. So this couldn't happen, that you could have a right angle somewhere else down the road. So the right angle couldn't have been down the road, it had to be right here. That's the logic that it's saying. Okay? Does that make sense now? Now, the other way to do this is to talk about if you started with a right angle, then prove that it's a tangent line. And that's the same concept. That you assume that you don't have a tangent line at the right angle. So here's my secondary proof of this one. So you start with a circle, and you start with a circle, draw your line, right, you draw the right angle, so we're assuming that this, this radius is right angle to the tangent line. But now what you do is you assume that when you draw a right angle, that this line is not tangent. So we're going to start with the opposite fact, not the fact that we're starting with that no right angle. We're starting with the right angle, but we're going to assume that the blue line that I've drawn at the bottom is not tangent. So at some point down the road, so if this is truly not tangent, that means at some point down the road, I'll hit another spot if it's truly not tangent. So let's call this A, let's call this B. Okay. So if that's truly a 90-degree angle, then and that's not a tangent line, then at some point down the road, I'll have another one, right? So I'll put the right angle over here. That looks terrible, but go with it. So we'll draw another line, and these lines are the same length, correct? Because they're both radii to the circle. So that means that this triangle is isosceles. It's isosceles. Two walls are the same. Because they're radii. Well, if you have isosceles triangles where two walls are the same, that means two angles have to be the same. So that means the base angles. These are the base angles. So that means both angles in that triangle have to be right angles. You can't have that. You can't have a triangle with two right angles. It's not a triangle. It's like a box that's open. Like it's not a triangle. So the idea is that we just found out that's the moment where we did something wrong again. Like it doesn't work. So the whole idea with what I'm showing you here is that for this truly to be a tangent line, for this radius to be truly a tangent line, that it has to be perpendicular to the radius at that exact spot. That's the whole concept. So I'm showing you like the definitive way to prove it. Now, typically you would never see that until you went to like a college level math course. I'm just letting you know that. So that's just something like that's the definitive way that they prove things. They use an indirect proof of it. All right, we're good with theorem 1011 or 1010. Okay, all right, we're done with that one. That one's pretty easy. Let's do 1011. This is our last one today, and then you'll have the rest of the time today where you can actually work on your assignment. All right, perfect. All right, nice stuff. All right, we're going to do theorem 1011 now. Theorem 1011. A point exterior to a circle in the same plane of the circle contains two tangents to a circle. Okay, I'll let you write that down. I think I wrote this correct. I think I wrote the paraphrasing, right? Okay, yeah, I'm paraphrasing a little bit. Okay. They say a point exterior to a circle in the plane of a circle, the tangent line to the point, the two tangents are congruent to each other. That exterior point, whatever. So, a point exterior to a circle in the same plane of a circle contains two tangents to a circle. And they're actually the same tangent. They're actually congruent. So maybe I'll put a little hashtag. The tangents are congruent. Okay, that's the concept, right? So let me draw a circle. And I'm going to put a point exterior to the circle. It's outside the circle. Okay, that's my point. Let's call it point P. That's my circle. Let's call it circle A. Okay, so what this theorem says, you have a point that's exterior to the circle. It's on the same plane of the circle. It's going to contain two tangents to the circle. Well, duh. I could draw tangent lines, right? I could draw a tangent going this way. There's one. And I could draw another tangent line. Going that way. Well, what they're saying is that these tangents, these actual segments, if you were to draw these, they're actually the exact same length. But the red line and the blue line have to be the same number. Okay, it's going to use theorem 10-8, which is right angles inside of circles, and it's going to use this whole idea of the last one, which was tangent lines are perpendicular to the radius. So to prove that the red line and the blue line are the same, top and bottom line, let's give these names. Let's call this point B, let's call this point C. So we're going to try to prove that CP has to equal BP. That's what we're going to try to show. All right, how do you do this? You draw a radius right there, and you draw a radius going from A to B, right? Because A is the center. Okay, boom. So according to the last theorem, if it was 10-10, these have to be 90s. Okay, you're absolutely right. That was the last theorem. That was 10, right? You have right angles at that point of tangents. Okay. Now I'm also going to draw an extra line in the middle. I'm going to draw a line going here. From A to P. That's just a segment. I can put a ruler down, connect the lines from A to P. Because I think there's a corollary or a postulate we had that says through any 2 points you draw one line. So I can draw a line from A to P. I can actually prove that the two triangles are equal. I can actually prove that the two lines or the two triangles are equal, because the radii of the circle are equal, correct? The radius from A to C, A to B. They have to be the same stick. We have the right angle, so it is a right triangle. These are legs, by the way, of that right triangle. And the other wall that they both share, both triangles share, they share this wall. That's called the reflexive wall. Well, it's also the hypotenuse of the right triangles. It's the longest side of the right triangles. The right angle's here, that's the hypotenuse. The right angle's here, that's the hypotenuse. So, according to our HL theorem, hypotenuse-leg theorem, if the hypotenuse and leg of one right triangle is equal to the hypotenuse and leg of another right triangle, then the two triangles are equal. Okay, so boom, the triangles are equal, so that forces those to be the same. And that's the idea. That a point exterior to a circle in the same plane of circle contains two tangents. Boom, it does. It has two tangents to the circle, but they're equal. They're equal in length. Questions, comments, how to do this? Okay, now you're thinking, okay, why? Okay, I try to talk about, bicycles and cars and all that good stuff and, what uses tangents. This is the concept that we use to figure out how far stars are away from Earth. This is the exact math that's behind it. Because if you actually have the diameter from the top to the bottom, like how big the star is, and the angle that's in between the top and the bottom of the top line and the bottom line from looking at the top of that star to the bottom of the star, which is a really small angle because stars are really small in the sky, that if you have that angle, which is crazy small, and you have the diameter for that star, which is also crazy small, you can actually guesstimate the distance to the actual object. And that's what we use. That's like the concept of how they guess, like, oh, okay, this planetary system is 14 light years away. Light year is a term of distance that light travels in 1 year, right? That's a really far distance, by the way. So, I think the closest one they ever found that has planets around a star is like 7 light years. But again, I think I did a calculation on it years ago where 7 light years is like, if we're traveling at normal human speed, is like 300,000 years or something like that. Because in space, we can travel about 20 to 30,000 miles per hour, when we do slingshot effects and stuff. So currently at our speed, we wouldn't be able to get there in our lifetime. But NASA said like a couple months ago that they can send a probe into space, a very small probe, an AI intelligence robot that's really small. It can get there in like 20 years. I was like, wait, what? It takes like a couple 100,000 years to get there. Because the probe is so small, it can break that speed limit that humans have. Because humans have like that speed limit of like 20,000 miles an hour, so many G's before your body kind of shuts down. You can't handle it anymore. But a robot can. So they can send a probe out in space and get there in 20 years, check the place over, and then come back and take another 20 years to get back. So I thought that was kind of a cool concept. So I think that's the project they're working on. I don't know if they've actually launched that yet, but I think when they did that, they said they could be there as early as like, I think it was 2025 or something like that. That could be the earliest they could arrive at this certain exoplanetary system that really makes Earth. So kind of cool concept. I really like following that stuff on NASA because this is the concept they used. I mean, that's how they figured out the distance to that planetary system. They're like, we could go there. Okay, well, fair enough. So, kind of cool concept, but all good stuff. All right, homework due Monday. That's your page 727. If you already have it done, wrapped up, finished, however you want to say it, that's fine. Turn it in the basket, please. Put your name on it. If you have any other light work that you want to turn in, make corrections on, you can do that. I'll probably update your grades over the weekend. I know some of you have actually turned in today's assignment. I'll check them, put them in the group book. So if your parents check your grades on Sunday night, you're missing something, it's probably that one that's due Monday. So tell them to calm down, it's due Monday. So some of you have actually turned in, so I'll grade it if you have. So. All right, well, there you go.